College Algebra, Module 6, Topic 6.3, Polynomial Functions and Models. Objective 1, Polynomials and Turning Points. A polynomial function f of degree n can be expressed as the function f of x equals a sub n x to the nth plus all the way up to a sub 2x squared plus a sub 1x plus a sub 0, where each coefficient a sub k is a real number, a sub n is not 0, and n is a non-negative integer. This is exactly the same function we talked about in the previous topic. A turning point occurs whenever the graph changes from increasing to decreasing or from decreasing to increasing. As a note, a local extremum is a y value, not a point. However, a turning point of the form x, y is a point on the graph. When we talk about polynomial functions, we can talk about polynomials of degree 0. That means there is not an x term. A polynomial function of degree 0 has no x-intercepts and no turning points. Some examples are these two functions. This one is f of x is equal to 4, and this one is f of x is equal to negative 3. A first-degree polynomial function, also called a linear function, is a function of the form f of x equals a sub 1x plus a sub 0. And as before, you're probably used to seeing this one look like f of x equals ax plus b. A first-degree polynomial function has one x-intercept and no turning points. These are examples of first-degree linear polynomial functions. A second-degree polynomial function, also called a quadratic function, looks like this. F of x equals a sub 2x squared plus a sub 1x plus a sub 0. You are probably familiar with this one as ax squared plus bx plus c. A quadratic function has 0, 1, or 2 x-intercepts and 1 turning point. Here are some examples of quadratic functions. The first one has no x-intercepts, the second one has 1 x-intercept, and the third one has 2 x-intercepts. But notice all three of them only have 1 turning point. We also have third-degree polynomial functions, also called cubic functions. And these are functions of the form f of x equals a sub 3 x to the third plus a sub 2 x squared plus a sub 1 x plus a sub 0. Now, cubic functions have 1, 2, or 3 x-intercepts, and they will either have 2 or 0 turning points. Here are some examples of cubic polynomial functions. Fourth-degree polynomial functions are also called quartic polynomial functions. Notice these are the typical polynomial formula. The highest power is x to the 4. The leading coefficient is called a sub 4. We must have the x to the 4th term. Then we can also have an x to the 3rd, an x squared, an x, and a constant term. Now, fourth-degree polynomial functions can have up to 4 x-intercepts and up to 3 turning points. Here are some examples of fourth-degree polynomial functions. Now notice that on all three of these pictures, both of the ends are going in the same direction. In the first picture, both ends go upward, but in the second and third pictures, both ends go downward. Now a fifth degree polynomial function, or a quintic function, is our standard polynomial function. Degree 5 means the highest power is 5. A sub 5 is the leading coefficient, which is the number in front of our x to the fifth term. Again, it must have an x to the fifth term. All of the other terms are optional. We can have them in our function or not. A fifth degree polynomial function can have up to 5 x-intercepts and up to 4 turning points. Here are some examples of fifth degree polynomial functions. Now notice on each of these, the end directions, one will go up and the other one will go down. Okay, so let's go back and sort of talk about the similarities and the differences of all of these polynomial functions. First of all, the function f of degree n that is greater than or equal to 1 has at most n minus 1 turning points. This means that if a graph has 2 turning points, then it has a minimum degree of 3. Which says if a graph has 5 turning points, then it has a minimum degree of 6, which means it's either of degree 6, 7, or higher. Now, end behavior is what the function does far to the left and far to the right. The end behavior depends upon the degree of the polynomial and whether its leading coefficient is positive or negative. Objective 2 is how to determine end behavior. Well, if a sub n is greater than 0, that means the leading coefficient is positive. Then if it's of even degree, then both end directions will go up. If the leading coefficient is positive and it is of an odd degree, then the polynomial graph will go down to the left and up on the right. Now, the second one says if a sub n is less than 0, which basically says if the leading coefficient is negative and the degree is even, then both of the endpoints will go down. And then the last one says if the leading coefficient is negative and you have an odd degree, then the graph will go up on the left and down on the right. It's like we mentioned earlier. If the degree is an even number, both ends will either go up or both ends will go down. If the polynomial has an odd degree, then one direction goes up and the other goes down. Let's do an example. Describe the end behavior of the polynomial f of x equals negative 7x to the 6th plus 3x to the 5th minus 8x to the 4th plus 20x to the 3rd minus 11x squared plus 5x minus 9. If all we're looking at is the end behavior, we start out and say, well, the highest power is 6. Therefore, the degree is 6, which is an even number. So for our graph, they're either both going to go up or both ends are going to go down. Then we look at the leading coefficient, which is the number in front of your x to the highest power. If the leading coefficient is negative, that means that both ends will aim downward. So our graph, the left side goes down, the right side goes down, and then we're not really sure what happens in here. and it can have at most 6 x-intercepts, but right now we're just looking at the end behavior. So for our summary, if n is greater than or equal to 2 and is even, now remember n is the degree of the polynomial, which is the highest power. So if the degree is even and a, which is the leading coefficient, and a is greater than 0, then the graph gets larger and larger to the left and the right, which basically means that both ends are going up. If a, which is your leading coefficient, is negative, then the graph falls to the left and the right, which means on both directions they're going down. If n is greater than or equal to 1 is odd. So if we have an odd degree and the leading coefficient is positive, then the graph falls to the left and rises to the right. And again, we're not sure what all happens in the middle, but just looking at the end pieces. But if a is less than 0, so if the leading coefficient is negative, then the graph is going to go up to the left and down to the right. And lastly, the graph of f with degree n greater than or equal to 1 has at most n x-intercepts and has at most n minus 1 turning points. Let's do some of these examples. Identify the graph of f of x based on end behavior. Well, again, the highest power is 2, so we've got degree is 2, which is even, which means both ends are going to go up or both ends are going to go down. Because this is a negative x squared term, we know that the leading coefficient is negative 1. Therefore, we know that both ends of our graph is going to aim downward. The next example, f of x equals negative x to the 4th plus 3x to the 3rd minus 2x squared plus x plus 6. Well, highest power is 4, so we say that the degree is 4, which means they're either both going up or both going down. The leading coefficient is negative 1 because it's a negative x to the 4th. So again, both of these endpoints are going down. And then our last example, the highest power of this polynomial is 3. So the degree is 3, which is odd, which means one's going to go up and one's going to go down. If the leading coefficient is positive, then it's going to be increasing most of the way, which means it starts down and ends up. But for our case, the leading coefficient is negative because it's a negative x to the 3rd, which means it's basically going to be decreasing on the ends, so that it's going to go up on the left and down on the right. Objective 3. Graphing polynomial functions. Graph the polynomial in the standard viewing rectangle. Then find the turning points and identify any local max and min. So when we put this in our calculator, we get 4 plus 4x minus x to the 2nd power. Now, because it says graph this in the standard viewing window, we're going to go to Zoom 6, which is standard, and there is our picture. Is this what we expected? Well, the highest power was 2, which means it's an even degree, so either both go up or both go down. Because the leading coefficient is negative, that tells us that both endpoints were going to go down. Also, because it was 2, that told us that there was only one turning point. So we need to find that one turning point. Well, the turning point's up here at the top, which is our maximum. So we are going to go second trace, which is calculate, number 4, which is maximum. Left bound, well, our cursor is already to the left of the highest point, so we press enter. Right bound, arrow to the right until we're at least on the other side of the highest point. Guess, we don't need to guess, we just press enter, and that tells us that our maximum is at 2, 8. So our turning point is 2, 8. Because that is the highest point of the whole graph, the local max and the absolute max is going to be 8. Let's do another one. This time our function is negative x to the fourth, so we'll enter our function in as y1 plus 3x to the third minus 2x to the second plus x plus 6. So we press graph and our graph appears as shown. Okay, let's check. Does it make sense? Well, highest power is 4, which means the degree is even, which means either both are up or both are down. Because the leading coefficient is negative, because it's a negative x to the fourth, that tells us that they are both going down. We can have at most 3 turning points, and it can graph the x-axis in at most 4 places. Okay, so now we've got to find the turning points. Well, what we might want to do is zoom in because it's hard to tell exactly what's happening in there. So we can do zoom in, which is number 2. And when we zoom in, it takes the cursor wherever you put it and makes that the center of the next window. So if I'm trying to find what happens on these turning points, we put our cursor right here in the middle, we press enter, and it zooms in around that cursor. Now notice that there's really only one turning point because the graph is increasing, increasing, increasing. So there's our only point. So we're going to go through and say second calculate, or second trace, which is calculate. Number 4 is the maximum. I can go ahead and press enter right here for the first value. Then the second value, we've got to make sure we're on the right side of the highest point, and then we don't have to guess. So that maximum would be 1.76 and 8.33. Okay, again, this is our turning point, which is actually an ordered pair. Now our max is just this highest point right up here at the top. So our local max and our absolute max is going to be 8.33 because that is the highest point on the whole graph. Okay, let's do one more of these examples. So we're going to go up to y equals, and we're going to enter our function 5x minus x to the power of 3 plus 7x. And let's go back to zoom 6 to get us on our standard viewing window. Now, that one's a little bit tricky because we can't see the highest point nor the lowest point. That makes sense to us because the highest power was 3, which means that the degree was odd, which means that one end goes up and one end goes down. Because the leading coefficient is negative, that means the highest point is going over to the left, and then the lowest point is going down to the right, which matches up with what our graph is showing. Now we need to find these max and min, the local max and min in our picture. So what we can do is we can either zoom out, which is zoom 3, and then press enter, or we could have just adjusted the window size. But this works. So we're going to go through and say second trace, which is calculate. To start with, we'll just say number 3 is the minimum. So So we're trying to find this lowest point right there. So it's asking us for a left bound, so we need to be on the left side of that lowest point. So we're going to go enter for the left bound. We're going to arrow right and make sure that we're to the right of that lowest point. No need to guess. Our first turning point is at -2, -16. Then we've got to find the turning point up here. So we're going to go second trace, which is calculate. This time it's the highest point, which is number 4. So we're going to go to the left, press enter. We're going to arrow over to the right, press enter. We don't want to guess, so we're going to press enter again. And the second turning point would be the ordered pair 2, 16. So there's our turning points. Then it says to identify any local max and local min. Well, our local max is that second ordered pair, which is a y value of 16. Our local min is the lowest point. How low does it go for this little area? And we said that the local min was -16. Notice there is no absolute max because the graph goes high to the left. There is no absolute min because the graph goes all the way down on the right. Objective 4 is polynomial regression. This is where we use our calculator to find a function that models the data. So for this example, the total number y of endangered and threatened species in the United States are given in the table for various years x. Find a cubic function that models the data. So we are going to go into our stat. First thing we want to do is edit. And then we're going to enter our years. Okay, because they don't tell us let x represent the number of years since 1980, we are just going to enter these 4 x values in as L1. So we've got L1 containing 1980, 1985, 1990, and 1995. Now for L2, we're going to put in our numbers, 786 for the first one, 941 for the second one, 1,181 for the third one, and 1,599 for the fourth one. Because it tells us that we want the cubic function, we can go to Stat, Calculate, and Cubic Regression is option number 6. So if we press Enter to get cubic and then Enter to do our function again, that gives us our formula. So y equals 0.124x to the third minus 736.72x squared plus 1,459,051.1x minus 963,219,912. So this would be our cubic function modeling this data. Our next example is to graph the following data. If you know the degree is either 1, 2, or 3, see if you can determine the degree of f. So we are going to go into Stat. First thing we're going to do is go into number 4, clear list. We want to clear second L1, comma, and we want to clear second L2. When we press Enter, that clears those lists. So we're going to go into Stat, Edit. Our x values are going to be -3, -2, -1, 0, 1, 2, and 3. Then arrow over. Our y values, or our f of x values, are going into L2. So we've got 3, -8, -7, 0, 7, 8, and -3. So our first question is the degree going to be 1, 2, or 3? Is it linear, quadratic, or cubic? So what we can do is we can go into second stat plot, select enter to turn it on, enter. To select it, we can go to zoom 9, which is zoom stat, and we just want to see a picture of our graph. Well, you notice that the graph comes down and then it goes back up and then it comes back down. Well, if it was of degree 1, it's linear, and this is obviously not linear. Degree 2 is a parabola, and this is not even the shape of a parabola. So this tells us by looking at the picture that this data is of degree 3. Okay. Also, we can look at it. We know that there are 2 turning points as the graph goes from left to right. Then the minimum degree would be degree 3. And then finally it says write a formula for f using that minimum degree. Well, we're going to go into stat. We're going to calculate. Again, cubic regression is number 6. So when we press number 6 and then press enter, that gives us our formula, which says f of x is equal to -1 x to the third plus 0x squared plus 8x plus 0, or -x to the third plus 8x. And we could check it on our calculator. We could go up to y equals, and we could enter our function, -x to the power of 3 plus 8x, and hit graph, and our graph should go through all of our points, or at least most of our points. Okay, our next example, the total number of endangered and threatened species is given in the table below for various years. Use regression to find a polynomial function that models the data where x is the number of years since 1980. Well, that tells us when we're doing our chart, we are going to let the first value be in our calculator 0, since 1980 is 0 years since 1980. 1985 would be 5 years after 1980. 1990 would be a 10, 1995 15, 20, and 25. So it's important that we do that first before we start putting the values in our table. So we're going to go into stat, and we are going to enter the values. We need to graph this so we can identify which degree function we are looking for. So when we do that, we can just go to second stat plot, choose enter, enter, and then we're going to go to zoom 9, which is zoom stat, and that looks pretty linear to me. It looks a little more linear than it does anything else. So we're going to go stat, calc, number 4 is linear regression. When I do, I get a linear regression equation with A and B. I'll tell you what I'd like to do is go back and do second catalog. Go all the way down to diagnostics, turn our diagnostics on, because if you'll remember, that gives us R. So if we go to stat, calc, number 4, enter, that says that it's a 98% fit to a linear equation. So our formula was f of x is equal to 45.85x plus 772.76. So when we use f to estimate the number of endangered and threatened species in 1998, the first thing we have to do is determine the number of years since 1980 it was, which is 18. So now we're going to go f of 18, which is 45.85 times 18 plus 772.76. So we would get 1,598.06, which is approximately 1,598. Then the next question says, estimate the year when this number reached 1,600. Well, what we're going to do is we're going to go back up here to the formula and we're going to plug in f of x is 1,600. Well, when we do that, we're going to subtract 772.76 from both sides, which gives us 827.24 is equal to 45.85x. We're going to take that number divided by 45.85, and that would give us 18, which is 18 years after 1980. So we've got 1980 plus 18, which would give us a year of 1998, which that makes sense because 1600 is between 1995 and 2000. Then the last question says, was this interpolation or extrapolation? Well, because it was between two table values that we knew, this would be interpolation. You are now ready to do the homework for Module 6, Topic 6.3 in my Math Lab. Once you have scored at least 90% on all of these homework sets, you will be ready to take the Module 6 quiz. Remember, you must have notes from all three sections in order to take the quiz.